Hello everyone. Today we will exploring the fascinating topic of investigating trace elements in nanomaterials using ICP-MS. Before we dive into the details of our topic, let's take a moment to introduce the team behind this presentation. First member is Dini Iskandar binti Ben Patang and me, Siti Nurkaya binti Zainuddin.
Assalamualaikum warahmatullahi wabarakatuh and hi everyone, I'm Dini Iskandar bin Patang. So before we jump into the further topics, I want to ask you, have you ever wondered how a tiny particle can revolutionize technology, medicine and environment? What is the nanomaterials or nanoparticle itself? So nanoparticles are the trace element that can affect the material's performance, stability and even toxicity. So right now, nanomaterials are the transforming diverse fields, from the catalyst to the biomedical device due to their unique properties. That's why we want to know what is the nanoparticle. The importance of nanoparticle itself to us to characterization in the sample. So we have two factors. First, by determining the nanoparticle size, composition and concentration, it can make us to understanding the properties of nanoparticles. Other than that, we can see the nanoparticles right now influence on the application, directly impact use in the medicine, electronic and environment monitoring. So we use ICP-MS to know what the nanoparticles characterization. Role of the ICP-MS itself provide the both qualitative and quantitative data to us and also support the effective application in consumer goods, pharmaceutical and other industry.
Hello, my name is Siti Nurkaya binti Zainuddin. I will continue to the lesson. ICP-MS is the preferred method for nanoparticle analysis due to its unique capabilities. First, it allows for the simultaneous detection of multiple elements, making it efficient and comprehensive. Second, it offers reduced functionality, meaning it can analyze both dissolved and analyzed nanoparticles in the same sample. Lastly, its exceptional sensitivity and throughout make it suitable for a wide range of application from environmental monitoring to industrial quality control. These features ensure that ICP-MS stand out among the other 10.
Let's explore the key advantages of ICP-MS in more detail. First, multi-element detection. Unlike other methods, ICP-MS can identify several elements at once, saving both time and resources. Secondly, sensitivity. Its ability to detect elements at parts per trillion levels ensures even smaller traces are identified. The third one, isotopic analysis. This feature provides the critical insights such as the origin of materials or isotopic variations. Lastly, speed with its high sample through output. ICP-MS can handle large volumes of data efficiently. These advantages make ICP-MS an indispensable tool in the nanoparticle research and
Where other
beyond.
techniques such as dynamite like scattering DLS or differential quantification are commonly used for the nanoparticle studies that have several limitations. First, they lack the ability to determine the limiting composition. Second, they often require extensive and time-consuming sample preparation. Lastly, their resolution is lower, especially when dealing with the complex samples. ICP-MS overcomes these challenges by providing detailed, accurate, and high resolution analysis with the minimal sample preparation.
We will explore how spectral analysis helps identify and measure elements in samples using qualitative and quantitative analysis. Qualitative analysis tells us what elements are present using their mass to charge ratios. Techniques like ICP-MS make this fast and precise. Quantitative analysis measures how much of elements is present, which is key for research and safety applications.
As we know, ICP-MS can give a data about the nanoparticles and size distributions. So also the particle number of concentration. As we see in the figure 1 shows the schematic diagram of the particle transport from the sample into the ICP-MS interface and resulting in the time evolved signal generated by the mass spectrometry. So in how nanoparticle size and distribution being read. So IPCMS in the single particle mode measure the ion plumb generated by the atomization and ionization of individual nanoparticles. It can give a size. So size is determined by the calculating the spherical volume equivalent diameter using the mass data corrected for the density. About the particles number concentration, by quantifying the number of nanoparticles per unit volume, IPCMS can also provide insight into the sample homogeneity and dispersions.
IPCMS also can give the elemental composition read. So IPCMS identify the element within the nanoparticle by analyzing their mass to charge MZ ratio, and this capability is essential for the detecting a core element and coating in the complex matrix. As we see as an example in the figure 3, by expanding the view of signal of the two silver nanoparticle event, the baseline between the particle, which is a dual to the dissolved Ag, must be subtract before calculation of nanoparticle mass. Due to the data not to overlap to each other, integral dwell time is introduced. So what the effect of integral dwell time gonna do to our data? As you can see in the figure 4, dwell time is much longer than the particle plumb duration in A, which is A, ideal situation, entire single particles is captured with the integral signal time. B is acceptable, no particles are present during the dual timing, and C must be avoided because the particle is split into the two dual time. E must be avoided too because the two particles within the single dual time with the result in the double of signals, double the signal of the single particles. In the figure 5, we can see the resulting mass spectrum due to the introduction of the signal over each dual time, the approximately particle size from the example in the figure 4. So what we can say, dual time and the particle plumb has a consideration. First, on the short dual time, where its plumb duration is longer, can cause a negative size bias, missing the small signal at the distribution edges. For the long dual time or short pull duration, can increase the background signal, risk the counting multiple particles leading to the overestimate size distribution and underestimate particle count. So how you can control this? By control the particle flow rate, adjust the sample flow and dilution. 1/10 dual period should be contained in the single particle. That's how we can get a good data. So in the figure 6, we can see the good data and it's easy as to read. So in figure 6, a single nanoparticle event acquired using the fast time resolution analysis TRA mode with the 100 micro-s dwell time and no setting time, shaded the area representing a total of ion, count the sum of the 5 dual periods. The smaller the area in the rightmost dual period could be lowest in the baseline noise under the less than the ideal condition. So we can see figure 6 show a good read of data. That's conclude the dwell time is ideal for us to use the short dwell time and the longer plumb duration because the negative bias size. This reason because of the small signal in the Gaussian distribution edge are missing. Other than that, after we get the TRA data, right, how we gonna get into the size distribution? So data analysis For the single nanoparticles, wherever need to perform in the Microsoft Excel or in integrate instrument software, is roughly after we get the TRA data, we need to do a process into the Microsoft Excel. So the step include to 7 steps. After the TRA data, we need to collect a data as the figure 7a, second background correction, followed by signal integration, nebulization efficiency calculation, data sorting and visualization in the figure 7b, particles count calculation, and lastly size distribution profiling on the figure 7c. So we can see by get the TRA data, we can convert into the response vs frequency and convert to the size distribution. So that's how we get the ICP-MS to read our size distribution.
The data accurate or not? So comment on the data accuracy and precision. We can say the advantage that we get is of course ICP-MS itself have a high resolution and sensitive, ensure the precise measurement of nanoparticle down to 10 nanometers. And of course they have a limitation on the data accuracy and precision, that we assume that spherical particle shapes potentially skewing the data from irregular shape particles. Metric effects and interference like polyatomic interference maybe affect the result. So what we can do, we can improve by use the triple quadruple ICP-MS for the interference reduction and helium conciliation mode to enhance the accuracy.
Inductively coupled plasma mass spectrometry or ICP-MS offers several key advantages in the analytical science. Let's take a closer look at these benefits. First, high sensitivity. This technique enables the detection of ultra-trace elements, making it incredibly powerful for identifying substance at very low concentrations. Secondly, flexibility. ICP-MS is very versatile and applicable to a wide range of sample matrices. It requires minimal preparation, allowing for efficient and diverse analytical applications. Lastly, precision and accuracy. With the use of the internal standards and advanced calibration techniques, ICP-MS achieves a remarkable precision and accuracy in its measurements. Together, these advantages make ICP-MS a preferred method for elemental analysis in the fields such as environmental science, pharmacology, and materials testing. Despite its many advantages, ICP-MS does have some limitations. The first one, metric effects. Sample with a high salt content can interfere with the plasma ionization process, leading to the less accurate results. Secondly, operational costs. This equipment is expensive and skilled operators are needed for the effective use. While this challenge exists, they are being addressed through the advancement in technologies and analytical. Researchers are continually improving the capabilities of the ICP-MS. Here are some of the latest advancements. First, improve the ionization. Using mixed gas plasma such as argon helium, reduce the interference caused by the matrix effects. Secondly, automated sample preparation. Automation minimizes errors and ensure the consistent results. Lastly, enhance the detectors. Times of flight, the analyzers and other advanced detectors improve both the resolution and sensitivity. These innovations are making the ICP-MS even more robust and reliable for the nanoparticle analysis.
In conclusion, ICP-MS is a game-changing tool for nanoparticle characterization. It provides a comprehensive and precise data, offering insights into size, composition, and concentration, all critical for both research and industrial application. Its key advantages such as high sensitivity, multi-element detection, and isotopic analysis make it a standout technique in the field. Thank you for your time and attention.